Welcome back, Physics 11, to another exciting episode of Physics Notes with Mr. Wellsby. So this video we're going to be talking about two of Newton's three laws. So Isaac Newton was a brilliant physicist, well ahead of his time, maybe one of the smartest humans that ever lived, and he came up with three laws of motion, which very accurately describe everything up until the age of Einstein. We start talking about relativity, and we see that there's just a bit more to the puzzle than we initially thought. But Newton was definitely basically the only person to go to for those ideas for quite a few hundred years. So let's take a look at Newton's three laws. So the first law, just to give you it briefly, is as follows. An object in motion remains in motion and an object at rest remains at rest unless acted upon by an outside force. So this law is often referred to as the law of inertia. It basically says things that are moving are going to keep on moving unless something from outside goes ahead and applies a force to stop it or to change its motion. The next of Newton's laws, which we're not going to go into too much detail today, but I will let you know what it is. It's essentially this as a statement. Acceleration of an object is proportional to, that's what this symbol means, proportional to the force. Let me just clarify. Proportional to a force. So we most often see this written down as a formula, and that formula is F equals m times a, which is mass times acceleration. And what this top statement here means, acceleration is proportional to force, it means that if we say, for example, if we double the force on an object and the mass remains constant, then we're going to double the acceleration. If we have half the force, we'll have half the acceleration. So if you were to look at a graph, if we say it's proportional to, if we were to look at a graph, the graph would look something like this. The more force I apply, it should be the other way around, the more force I apply, the more acceleration an object is going to have, and that will be a proportionate relationship or a straight line through the origin. So that's the second law. And the third law is, I'm sure you've probably heard it before, for every action, which essentially means force, there is an equal and opposite reaction. I'm just going to put in brackets there, a reaction force. So for every action or every force, there's an equal and opposite reaction force. And if we wanted to have a formula for this, it would be as follows. Fa equals the negative of Fr. So if there's an action force, there's going to be a negative reaction force. And so, for example, if we push something down, there's going to be an equal and opposite force of pushing back up on us. So let's take a look at the first law. So essentially what this law of inertia is saying in broad terms is that inertia can be roughly defined as a resistance to a change in motion. So things that are moving want to keep on moving, and things that are stationary want to remain stationary. If that motion is going to change, it's going to require someone or something to apply an outside force to change that. Another way of saying that is kind of the way that's more helpful when we're thinking about trying to solve calculations or problems or things along those lines is as follows. If there is no net force on an object, then it will stay at a constant velocity. And keeping in mind, if it's not moving, it does have a constant velocity, and that constant velocity is 0. So not moving means that it's a constant velocity of 0. And if you think about it this way, this is probably the most helpful way of understanding Newton's first law. So for example, if I've got an object that has one force pulling up on it and one force pulling down on it, and those two forces are equal and opposite, there is no net force. And if there is no net force, then that means that there's going to be it'll be a constant velocity, and a constant velocity, again, another way that we can write this, constant velocity means no acceleration. Now, one common misconception is thinking about this as saying if the forces are equal, it's stationary. And that's not always going to be the case. It could be the case, as we see here, if it's not moving and the constant velocity is 0. But for an object that's already moving, if there is no net force, so that's either there's no force acting on it at all, or there are a number of forces that completely cancel out, like we can see on this diagram on the left, in both of those cases, it just means that it's not going to accelerate. It does not necessarily mean that it's going to be stopped. So you could still be moving at a constant speed, just like we can see here. An object that is in motion remains in motion. It's not going to change its motion if there is no force. So imagine if you were racing around a track on a go-kart, or if some of you have your driver's license, imagine driving around a corner or driving around a racetrack in your car. What would be 3 times that you would notice your inertia or notice some sort of force that's requiring you to change your velocity? So pause the video if you need to think about that for a minute. What are 3 times that you'd notice your inertia? In other words, 3 times you would notice a force acting on you in order to change your velocity. So in this case here, hopefully you pause the video to think about this if you need to. There's 3 cases that we can think of right away. One is going to be speeding up. Then you're going to feel, if you are speeding up, then you're going to feel that force pushing against your back. So you have that your seat pushing against your back when you hit the gas pedal. Another example of that is going to be slowing down. And if you brake very suddenly, you'll notice that change in your velocity, and you'll notice that being caused by a force which is from the seatbelt. So the seatbelt pushing back on you, that's going to be slowing you down. And lastly, there's also going to be turning a corner. So whenever you're turning a corner, you're also going to feel that force. So if you're turning really quickly to the right, if you're in your car, you might feel pressure from the car door pushing you left. And so there has to be some sort of force pushing you in order for you to change your velocity. And that's what Newton's first law is all about. So again, let's look at these examples here. So we have an example here in a book sitting on a table, and there's a force of gravity pulling down on the book, but there's also a normal or supporting force pushing up on the book. So what is going to happen to this book? So let's take a look here. This is our table, and on our table we've got a book that's sitting on top. It's a physics textbook, why not? And there's 2 forces acting on it. We've got the force of gravity acting down on it, and then we've got a force, we're going to call this Fn. This is a normal force, and this is Fg, the gravitational force. Now, if we look at these 2 forces, the book is stationary, right? And the reason why it's going to be stationary, hopefully you can see this here, is that there is no net force. And if there is no net force, that means that therefore, I'm not sure if you've seen a symbol before, but 3 dots is a shorthand mathematical way of saying therefore. So therefore, no acceleration, and therefore it will remain stationary. Okay, what about a case where there is a book that's being dropped? So in this case here, if I draw this textbook again, what are the forces acting on this? Well, it's not sitting on top of a desk, so really the only force acting on it, if we're ignoring air resistance, the only force acting on it is going to be the force of gravity. And in this case here, if we have an unbalanced force means that it's not canceling out, it's not equal to 0, then the book will accelerate. So what does the book do? It accelerates downwards. All right, so again, still applies to Newton's first law. If we have a net force on it, a net force will result in some sort of acceleration, and no net force results in no acceleration like the first example. Now I want to do a side example here. Let's say you are on a big sheet of ice, and on this big sheet of ice, you've decided to throw your textbook. Now we're going to pretend this is a perfectly frictionless sheet of ice. There's absolutely zero friction on this whatsoever. So if I have no friction acting on this, what are the forces? We're still going to have Fg, and we're still going to have our normal force. So these two forces are acting on it. But if it's sliding to the left or right, and I'm not pushing it, so I'm not pushing it, I'm not applying a force, there is no applied force over here, that doesn't exist. And there's also, like I said, no friction, so there's no force pulling it to the left. Is this what's going to happen to the book? Now in this case here, if there's no net force, it means there's no acceleration. But if this is already moving to the right, so you've thrown this book across the ice, it's sliding across this perfectly frictionless ice, is it going to have to stop? And the answer to this one may be surprising to you, but if this is an imaginary block of ice that's completely 100% frictionless, that doesn't really exist in the real world. But if we could somehow find a completely frictionless surface, in this particular case here, there's no net force, and so no net force means that it will continue at a constant velocity. So if we had a perfectly frictionless block of ice, this book would continue to slide forever and ever, or until some other outside force interfered with it. Okay, so here's some examples of it, and we can think about how these apply to Newton's first law. So while you're riding a skateboard, you fly forward off the board when you hit a curb or rock or other object that abruptly halts the motion of your skateboard. So in this particular case here, you, the object, you, the skateboard rider, are the object that we're referring to with the inertia. Now all of a sudden your board stops, but your body also has inertia. Your body also wants to continue moving in the direction that it was moving already, unless there's some outside force. So just because the skateboard has stopped doesn't mean that your body is going to immediately come to a stop with that. So that's why you would fly forward. So I'm not going to go over all these because you can certainly read them, but I do think it's a good idea if you can see if you can figure out how Newton's first law applies in these four cases. So we've already gone through the first one. You want to continue moving even though your skateboard has stopped, and that's why you'd fly forward off the edge of the board. And these are three other examples here of where we can use Newton's first law to understand something a bit better. So pause the video here and make sure you understand how these four examples apply to Newton's first law. Okay, so hopefully you've gone through that. And now we're going to take a quick look at Newton's third law. Now, Newton's third law, I'm just going to let you know ahead of time, this is probably the most widely misunderstood law. So this is the one that the majority of people kind of have a misconception that we're going to try and tackle today. So Newton's third law, again, just to repeat it, for every action, there is an equal and opposite reaction. And these actions or reactions are really just another way of saying force. For every force, there's an equal and opposite force being applied. And anytime we have these two forces acting together, we call them action-reaction pairs. Okay, so in this case here, we're going to take a look at the first one. So the first example here is you hit a baseball with a bat. So when that happens, and I'm going to write this in a very specific way so that we kind of get into the habit of thinking about it the same way. So the baseball, or the bat, applies a normal force So normal force is just a contact force between two solid objects. So the bat applies a normal force to the ball. And likewise, the ball applies a normal force to the bat. So what we've done in this case for the action-reaction pair is we have just simply switched around the two objects that are interacting with each other. But keep in mind, and this is the part that's often misunderstood, is the force that makes up the action-reaction pair is the exact same force between the exact same objects. So take a moment here and see if you can find the action-reaction pairs for example 2 and example 3. Okay, hopefully you have paused it, because this is a valuable exercise to make sure you understand this. Now a sprinter starts running. So what I'm going to say here is that the foot applies a friction force to the ground. That's how you push forward. And in this case here, the ground applies a friction force to the foot. So you push backwards on the ground with your foot, and the ground pushes forward on you. The ground pushes your foot forward. So you are trying to essentially push the ground forward, and the ground's trying to push your foot forward. So think about for a moment why it would be that you accelerate, even though the ground is remaining stationary or seems to remain stationary. So if we think about that, we are applying an equal and opposite force. So let's say I'm applying a 600 Newton force pushing the Earth backwards, and the Earth is applying a 600 Newton force pushing me forwards. Well, hopefully you can see that the reason why you would move forward as opposed to the ground is that you have a very, very, very small mass compared to the Earth. So even though you're pushing on the Earth and the Earth is pushing on you with the exact same amount of force, that's what Newton's third law is telling us, the amount of force is going to be the same, the Earth is just way too massive for you to possibly move, whereas you are definitely small enough for the Earth to move. So in this case here, that would be the action-reaction pair. And lastly, in this case here, the fish, I'm just going to call it applied force. So the fish has an applied force on the water, and likewise the water has an applied force on the fish. Okay, what about a bug hitting the windshield of a car? So pause the video here and see if you can answer these 3 questions. So there's bug hitting the windshield. What is the force pair that occurs? Which force is bigger? And which object has the greater acceleration? Okay, hopefully you paused the video and you've tried this question for yourself. But let's take a look what we have. In the first case here, the bug has a normal force on the windshield, and likewise the windshield has a normal force on the bug. Which of these forces is bigger? Well, this is a trick question. Both forces are the same. So which one is going to have a greater acceleration? Well, in this case, we can definitely know that the bug will have the greater acceleration, and that again is because it has much less mass. So this actually is an example of using Newton's second law. This is the law of F equals ma, and we can see here that the force is going to be equal for both. So in both cases, the force will be the same amount, whatever that amount happens to be. But for the bug, the mass will be much, much smaller, and therefore the acceleration will have to be much, much bigger in order to balance that out. So if the mass is 100 times smaller, then the acceleration would have to be 100 times bigger in order for it to equal the same amount of force. And again, here's just a few examples of Newton's third law in action. So not so much with a water gun, but if you ever fired a real gun, you would notice it has something called recoil or kickback. If you ever played any shooting video games, you see the action where your gun kind of pushes up towards the top of the screen, and that's because you are applying a force, or the gun is applying a force to the bullet, but that also means the bullet is applying a force back on the gun, pushing the gun backwards. Again, with the brick, we can see this as an example where you apply a normal force to the brick, but the brick also applies a normal force to your hand, which is why it obviously is quite painful. And lastly, for the rocket, the rocket is pushing out against the rocket fuel, but likewise, the rocket fuel is pushing back up against the rocket. So that's what causes that to rise. So hopefully you've learned something in this video, and as always, let me know if you have any questions. Thanks again.